on the open ocean, a ship is constantly pushed off balance by wind and waves. Surviving those forces requires absolute precision. A vessel's stability is a matter of life and death, leaving zero room for guesswork. To fight back against that rolling motion, a ship relies on something called the righting lever, or GZ. You can think of it as an invisible mechanical arm that actively pushes the hull back upright. Shipyards calculate the strength of this righting force based on different hull weights, providing the crew with a baseline reference. This is a chart showing the cross curves of stability, where this matrix of red curves gives the crew their starting data. A captain relies entirely on these calculations to survive a storm. But out on the water, this factory baseline is often dangerously inaccurate. The problem lies in the math. Shipyards build their cross curves using an assumed center of gravity, essentially a perfect theoretical blueprint. But the reality of commercial shipping is messy. Loading varying stacks of cargo and burning through thousands of tons of fuel physically shifts that center point upward as the voyage goes on. If the actual center of gravity sits higher than the shipyard's blueprint, the ship's physical defense against rolling is severely weakened. Before a captain can truly understand their risk, they must mathematically correct the shipyard's optimistic righting lever. Trusting uncorrected data creates a false sense of security. Determining exactly how much stability has been lost to the shifting cargo is the necessary first step to keeping the ship afloat. To find the real numbers, the crew starts by calculating the exact vertical difference between the shipyard's assumed baseline and their actual elevated center of gravity. They take that vertical difference and multiply it by the sine of the angle of heel. That equation produces a mathematical subtraction penalty. It gets applied directly against the shipyard's original, overly optimistic GZ values. The result of that subtraction is the corrected GZ. We now have the true righting lever for every possible angle of tilt. This isolated set of numbers is the essential raw material the crew needs to map out the ship's physical limits. The mathematical correction strips away the theory, leaving a customized, hyper-accurate profile of the vessel's current vulnerability in the water. We translate those raw numbers into the ultimate visual tool, the curve of statical stability. The architecture of the map is simple. The horizontal axis tracks the ship's angle of heel from perfectly flat zero to a 90-degree sideways roll. The vertical axis tracks the strength of our righting lever. The corrected data is taken from the table and mapped out dot by dot across the grid. Drawing a continuous line through these points reveals exactly how the ship will behave throughout an entire capsize event. Instead of parsing thousands of raw digits in a spreadsheet, the crew now has a single curving line that shows exactly how much punishment the hull can take. Looking at this statical stability curve, we locate the ship's absolute maximum resistance, max GZ, at the highest peak. By dropping a line down to the horizontal axis, we find the exact angle where the ship fights hardest to stay upright. We can also look at the steepness of the curve right at the beginning. Projecting that initial slope outward gives us the initial metacentric height, or GM, a measure of how stiff the ship feels during small everyday rolls. That peak defines the vessel's ultimate defensive capability. The moment the ship rolls past it, its ability to save itself steadily drops. Past the peak, the curve's downward trajectory tracks the rapid weakening of the righting lever as the ship is pushed further over. This graph shows the precise moment strength runs out. The intersection where the declining curve hits zero on the x-axis is the angle of vanishing stability. Pushed a fraction past this point, the curve plunges negative. The lever vanishes entirely, making capsize inevitable. The space between a perfectly flat keel and this final zero crossing is the range of stability. It is the literal mathematical margin between a successful recovery and total disaster. The righting lever is ultimately just a distance. To find the true physical force fighting the ocean, you multiply that lever length by the total displacement weight of the ship, yielding the moment of statical stability. By correcting the baseline data, plotting the curve, and calculating this final moment, mariners eliminate all guesswork regarding their ship's limits. By mastering this curve's mathematics, a crew takes the unpredictable, violent forces of the ocean and transforms them into a precise, survivable geometry.